Hey everyone, I think we're all here. Okay, so doubling it up here on the first day. Um, so I wanted to, thinking back to the lecture this morning, I wanted to just very briefly mention that as I go through these lectures, I'm going to be talking about a lot of different topics, and you'll hear me occasionally talk about certain articles or certain topics related to growth. Um, so it is never too early to start thinking about the topics that might interest you when it comes time to do your literature review paper, right? So, as I kind of talk about these things or mention certain articles or talk about certain ideas and it rings a bell with you, I was like, oh, that's interesting, or I'm kind of curious about that, or whatever. It would be great while you're taking notes to also note these kind of things, right? Like, oh, there's a topic or that's a paper or something about it sounds interesting. And then you can reach out to me and I can get you a copy of the paper or at least a citation for the paper, or we can talk about where you might go to, look for some more information related to that topic. So, for a paper like this, finding something that is interesting to you and exciting to you is half the battle, right? I mean, once you find something that's exciting and interesting and you find a couple of papers related to it, you really got a lot of the hard work done, right? And then it's just kind of a matter of understanding what you're reading and trying to make some sense of it. And so, like I said, it's never too early to begin thinking about what kind of interests you. And one of the things that I will definitely do as we kind of move through the material here is I'll be pointing out to you topics that might make good papers or articles that might make good papers or other references that might make an interesting topic. And so, take advantage of that, right? So you don't spend so much time spinning your wheels. What you don't want to do is the night before your draft proposals due say, what do I want to do? Because if you wait that long, then you're going to end up picking something that doesn't excite you, and you're probably going to end up picking papers that are either not interesting to you or don't really fit in with what you want to talk about, and it's going to make this whole thing not only much less of a learning experience, but a lot less enjoyable to do. So yeah, it's never too early to begin thinking about this, and we will also, like I said, we're going to have some people from the library come in, I believe, on Thursday, somebody from the writing studio come in on Friday, and we'll just keep on talking about this paper, keep it in the forefront as we go through the material, and I think that will hopefully, jog some interest for you so that we can, the sooner you get looking about topics and articles and, at least even finding one article that's really interesting to you. From that one article, oftentimes you can use that as a springboard to finding other articles that are useful to you. So anyway, so just keep that in mind as we go through stuff. So what are we going to do this afternoon? Well, in terms of full disclosure, this afternoon's lecture is probably not the most exciting lecture that we'll have in this class, almost certainly not. But we want to do a little bit of math review. So I would not say that this is a mathematically intensive course, but there are a couple of concepts that we need to understand when working with growth. And so, we're going to kind of put it all into one lecture, right? Kind of review most of the main tools that we need to use this block. And then, from there on, we'll use them as we go along. But just to kind of refresh our memory about some of the basic tools. For some of you, you'll find everything that we do this afternoon review, right? Just review. For others of you, it will be review, but maybe it isn't particularly fresh in your mind. And then for others, particularly those of you who have not taken intermediate macro, there's probably a few things in here that might look a little new to you. And, like I said, you can always ask me questions about it if you're confused, or most of what I'm talking about today comes from the appendix to chapter 1, appendix A to chapter 1. So you can also go back and take a little bit more time and look at that. All right, so without further ado, let's just jump in here and do our math review. All right, so the math that we're talking about here today really has everything to do with growth rates. And so how do you capture mathematically what a constant growth rate looks like? So let's say we have y here. Y, in this class, we will usually use to denote per capita GDP. How can we express y per capita GDP at time t? Well, one way you can express it mathematically is to think about it like this, where y0 here is the initial level of GDP, right? And GDP at time 0, and g is the constant growth rate. And t is just time, right? So for instance, what is GDP in year 100? If you begin at GDP of 100 and your growth rate is 0.02, well, you calculate it like this. T is 100, right? 100 periods. Your growth rate is 2% or 0.02. Here would be initial output. You can use your calculator. Shoot, I don't have my calculator. Somebody's got a calculator here. You can figure that out. But that's how you would calculate a constant growth rate, right? That's how you calculate a constant growth rate, or what output is based on a constant growth rate. Now, the other way that you can do this is, when I did this equation, I assumed that you knew what the growth rate is and you're finding out what output is. But the other way is you could rework this equation and solve for what the constant growth rate is. Right? So you can solve this another way and figure out what constant growth rate is, the implied, and we call this the implied constant growth rate. Right? Implied because what are the two pieces of information we need to know? We need to know output in the initial period and output at the end of the period. And so this formula is a way to calculate what the implied constant growth rate is between two time periods. So think of a simple example. This is actually an example using US data. In 1870, which is our initial period, output in the US per capita output was about $3,200 in 1870. Oops. How about in 2017? In 2017, output was roughly $54,000. Okay? So we know output at the beginning of the period, we know output at the end of the period. What's the implied constant growth rate? Right? It's just the ratio using this formula here that we just derived. It's just the ratio of 54,000 to 3,200. And there is 147 periods between them. Okay. Break out our handy dandy calculator. What do we get? 0.0194, or about 1.94%. So I told you this morning that per capita GDP in the US has averaged a little less than 2% a year. This is where I got that number, right? So if you just take GDP back in 1870 and take GDP today and use this implied constant growth rate formula, you can figure out what the growth rate is between any two periods. periods. Why isn't the growth rate this? Why can't we calculate the implied constant growth rate like this? Just take the percent change in GDP and divide it by the number of periods. In other words, what we're doing here is we're calculating an average growth rate. What's the problem with doing it this way? What are we missing? Any idea? Anybody got an idea about what we're missing if we do it this way? This way is ignoring compounding. You're ignoring the fact that output growth from 1970 to 19, or it's from 1870 to 1871 is then going to grow in 1872 and is then going to grow in 1873. So this is just an average growth rate, but that is not what we want to calculate. We have to account for the fact that growth compounds over time, right? So we have to figure that into our formula for getting the implied constant growth rate, right? And so the implied here is implied based on compounding, right? Based on compounding. So this does not work, right? This does not work. We do not want to do this. We want to use this formula, right? That takes into account compounding. So what is really happening in this formula, if we think about what's happening over time, what's happening in this formula is if we have time here and output there, we start here at output in time 0. What's happening to output over time? It's rising, and it's rising at an exponential rate. So what our growth rate formula here incorporates is exponential growth. There's a constant growth rate, but that constant growth rate explodes in levels. Why? Because of compounding, right? So the constant growth rate leads to an explosion in levels over time because of compounding. And so as we mentioned this morning, compounding is the key to understanding growth, right? When you're talking about growth, the key is compounding. This is the reason why small differences in growth rates lead to big differences in levels over time, is because any growth today will compound in the future again and again and again and again and again. And it's the same principle for those of you who are finance majors or just interested in saving. It's the same reason why saving today is so important, because the earlier you save, the more time that money that you put in the bank compounds, because the money you earn earns interest. The interest earns interest over and over and over again, right? And that's how you can turn a little bit of money into a lot of money over a long period of time, right? Through the power of compounding. And so whenever we talk about growth, we need to keep this forefront in our mind, right? That growth is all about compounding, right? And it's about exponential growth, right? So growth begets growth. Now, when we talk about growth over time, we also have to talk about the concept of derivatives, right? Calculus. How many of you have taken calculus? Just a little show of hands. Anybody? Let's see, 3. Let's see, a couple hands. Okay. Well, for those of you who have not taken calculus, don't worry, right? throw your computer out the window and run screaming from the room. This is not a calculus class. You don't need to know calculus. But I do think that having a little bit of intuition about what calculus is will be useful to us, right? And so really a derivative is just a change in a function. Right? In calculus, when you talk about a derivative, you're just talking about a change in a function as a variable changes. So let's think about a simple example here. Let's say we have a function y, which is a function of x, and this is a very simple function. Y is equal to 5x. Then what's a derivative? A derivative would be how y changes as x changes. Right? And we'd write that the change in y over the change in x, the change in y over the change in x, dy dx. And in this case, what's that? The answer? It's 5. If x changes by 1, then y changes by 5. That's a derivative. That's the derivative of this function. And in this case, for those of you who've taken geometry, the derivative is just the slope, right? So this is just the line, and the slope of the line is the derivative. So that's what a derivative is. Now, in this class, we are interested in a certain kind of function. We are interested in functions where what's changing? Time. Time is changing. Okay? So, in this case, we're often going to be talking about what happens to a variable as time changes. Instead of writing dy dt all the time, we're just going to call this y dot. Okay, that's the notation that your book uses. So instead of using dy dt, in other words, how a variable is changing over time, when we put a dot over it, it's basically talking about how that variable changes. This is approximately equal to this, right? The difference here is that this is instantaneous, meaning the interval of time is minuscule, right? Where this is what we would call discrete, right? Where there's actually a interval, right? As opposed to instantaneous, where the change is only right at the margin. And if that doesn't quite make sense, I'm mainly using that language to talk to you who've taken calculus. Those of you who've taken calculus, you're probably familiar with this idea of instantaneous, meaning the change right at the margin, or discrete, where you have a big interval of change. But you could kind of think about these as equivalent concepts, right? Y dot is really just the change in y over time, right? It's the change in y over dot, or over time. So if y dot is greater than 0, then what does that mean? Y is growing. And if y dot is less than 0, what does that mean? Over time, right? So output is growing over time, or output is shrinking over time. However, let's be clear here. Y dot is not a growth rate. It's only a change. right? So y dot is the change in y. It's not the growth rate. How do you get the growth rate? The growth rate is y dot divided by y, right? Because this is essentially equal to this, right? Approximately equal to this. So to get a growth rate, it's not just y dot. We have to take y dot and divide by y, right? That will give us a growth rate. So for instance, if you're told that y dot y is equal to 0.05, what does that mean? Y is growing at 5%. Okay. So the main idea here, I actually don't think there's really any, I hope that there's not any conceptual issues. The most important thing I want you to understand is what this notation means, because this is the notation when you read chapter 2 in your book, this is the notation your book uses, right? Instead of talking about delta y, right? For instance, those of you who've taken intermediate macro, all the time I talked about delta y, right? Or delta k, right? That's not going to be the notation your book uses. Your book is using this notation, right? That delta y is really what your book uses as y dot, right? It's talking about an instantaneous change, right? An instantaneous change, how y is changing over time. Okay, everybody kind of with me on that? Any questions? Okay, so you're all online. It's hard for me to pick up your body language if you're confused. So you got to say something if that's not quite registering. Okay, hearing nothing. Let's move on. Let's talk a little bit about logarithms, because logarithms are very useful in dealing with growth rates. Let me just remind you of some of the rules of logarithms. And once again, this is not a math class, so I'm not really going to get into what, the details or the why behind logarithms. In general, for this class, though, if we remember some of the rules of logarithms, that's all we need to know. So the rules of logarithms are, if you have a function where, for instance, z is equal to x times y, then what's the log of z? It's the log of x plus the log of y. So logarithms turn a multiplicative relationship into an additive relationship. Likewise, if z is equal to x divided by y, then the log of z is equal to the log of x minus the log of y. Okay, so logarithms turn a multiplicative relationship into an additive, a divisional relationship into a subtractive relationship. Here's another rule. What happens if z is equal to x to the b power? Then the log of z is equal to b times the log of x. So logarithms turn an exponential relationship into a multiplicative relationship, right? An exponential relationship into a multiplicative relationship. Okay, this one is less intuitive. Oops, I'm sorry, looking at the wrong thing. And this is really a rule from calculus. We're not going to derive this. I'll just kind of assert this rule. And for those of you who've taken calculus, you probably remember this rule. But if y is equal to the log of x, then what's dy dx? In other words, what's the change in y from a change in x? What's the derivative of y with respect to x? And the answer is 1 over x. And then finally, the last rule. And this is the one that we're going to use the most and appeal to the most. What happens if we take the same relationship we had in rule number 4, but now we make it time? What happens if both y and x are a function of time? What's dy dt? Right? What's the change in y with respect to time? Right? For those of you taking calculus, you might remember the good old chain rule, right? And the chain rule is, well, this would be the dy dx times dx dt. What's this? Well, in rule number 4, we know what this is. 1 over x. And what's dx dt? We've defined that as x dot. In other words, dy dt is equal to x dot divided by x. And what's x dot divided by x? What is that? That's the growth rate of x. Okay? So let me put this into words, what this rule number 5 is saying, so we can see the importance of this. If you take the log take the derivative with respect to time, you get a growth rate. If you take the log and you take the derivative with respect to time, you get a growth rate. So this is the way that we can work back and forth and write anything that's in terms of levels in terms of growth rates. Any expression that's written in terms of levels, we can turn into one that's written in terms of growth rates by remembering this rule. Take the log, take the derivative, you get a growth rate. Okay, let's use this rule to do an example. And this is an example we will use time and time again in this class. The Cobb-Douglas production function. Okay, good old Cobb-Douglas production function. This should be something that I believe all of you have seen. this is kind of a standard production function. In fact, this will be a production function that we use in many, many of our models that we develop in this class. And the Cobb-Douglas production function just follows this general form. Okay? Y is really a function of three things. Productivity, physical capital, and labor. And notice here that we have two exponents. And we'll talk a little bit tomorrow. We typically assume that these are 1/3 and 2/3. Why? Well, this is what the data tells us they are. And I'll kind of explain that a little bit more tomorrow when we actually look at some data that will help us. But this is a very standard production function that's used in economics, right? And here, what determines output? Forget to write that this is output. What determines output? Three things. How much physical capital you have, how much labor you have, how productive you are. Those are the three big things that determine how rich you are. Now, this is written in terms of levels. How do we write this in terms of growth rates? Well, let's use that rule number 5, okay? What's rule number 5? To turn anything from levels into growth rates, what do? Take the derivative, take the log, take the derivative with respect to time, right? So first, take the log of this. Remember, logs turn a multiplicative relationship into an additive relationship. So this becomes the log of AT plus, what's the log of this? What's the log of that? Remember, an exponential relationship becomes multiplicative. So this becomes 1/3 times the log of K. And what's the log of the last term? 2/3 times the log of L. All right, so we've taken the log of everything. Now that I do this. Sorry, I got screwed up. And then you take the derivative with respect to time. Or, once again, using rule 5, what is this? Y dot Y is equal to A dot A, K dot K, and L dot L. In other words, the growth rate of output is based on the growth rate of A growth of K and growth of L. It's actually, I should put in here to be more clear. It's a weighted average of these three things. It's a weighted average. So, hold on one moment. Let me pull up a figure here. And show you something. So let me show you that this is essentially how you can think about growth, as growth being based on a couple of different things. Population, which would be the growth of labor, right? Per capita GDP, right? And then total GDP, right? The components of output growth. So you have population, you have capital, and then you have productivity, right? Those are what we're often called the big three components, right? Those are the big three components that we will often refer to, right? And so, yeah, this is why this rule number 5 is useful to us, because as we know, we're going to need to talk about levels of growth, but also need to understand things in terms of growth rates. So moving back and forth between levels and growth rates is going to be very useful. How do we do that? Take the log, take the derivative, you got a growth rate, okay? So tomorrow, we'll get a little bit more practice with this, promise, right? As we work through the Solow model, we will do this a couple of times. And I hope after we do this a few times, I think it'll become second nature, right? Of how you can move between levels and growth rates. However, regardless of how confident you feel with the math, let me just say intuitively, this is a pretty simple idea, right? If output is based on productivity and capital and labor, what's going to determine the growth rate of output? The growth rate of productivity, the growth rate of capital, and the growth rate of labor, right? So intuitively, this is very simple, right? if the level of output is based on productivity, capital, and labor, then the growth rate of output is going to be based on productivity, capital, and labor, right? How do we take those growth rates and compute it back to the growth rate of output? Well, we have to take the weighted average. And so that's what this formula here is saying, is that the growth rate of output is just a weighted average of what the growth rate of productivity is, what the growth rate of labor is, and what the growth rate of capital is. Okay? All right, one last little math thing here, and then I'm just going to show you some data about how this can be useful. Logarithms are important for us not just to, kind of work between levels and growth rates, but they also help us visualize data. So logarithms are often very useful for us to help us visualize data. And this might be something for those of you who've taken data viz, you might be kind of familiar with this approach of, instead of putting data on a regular scale, you put data on what is called a ratio scale or a logarithmic scale. So it becomes easier to see what's going on. So let me explain to you what this looks like. Let's just take a simple function here. something that has exponential growth. And this time, instead of using output, let's use population. Okay. Shoot, sorry, this is wrong. What's the wrong thing? Okay. Here we have exponential growth. And if L is labor, then what determines our growth rate? Our initial population and N, which would be the constant population growth rate. Okay, so what does this function look like? Let's say we begin with a population of 6, and let's assume that the population growth rate is 2% or 0.02. So what's this going to look like over time? Well, at time 0, we began at 6, right? Let's use our rule of 70. So if population is growing at 2% a year, how long is it going to take to double in size? 35 years. 35 years. So in 35 years, we know that population is going to be 12. And where will we be in 70 years? Well, then the population will be 24. And where will we be in 105 years? Well, you can see the problem here. If I'm doing this to scale, I'm just blowing right out of my graph because we have exponential growth. We have exponential growth. So what happens when you try to just graph levels is it becomes very difficult to see what's going on, right? It becomes very difficult to see what's going on. And if you try to squish the vertical axis, if I can just do this, what happens if you squish the vertical axis and make this like 48? What do you see? Like nothing's happening, and then you have growth like that. You can't see what's happening in the initial periods because there's very little change relative to the later periods. So this is a problem with data visualization, is when you have things that are growing at an exponential rate and you just graph it in terms of levels, it becomes very difficult to visualize what's going on. So how can you solve that? Well, one way to do that is to do a ratio scale. In this case, a ratio scale would be, let's not make the units 1, 2, 3, 4, 5. Let's make the units a doubling of LT. In other words, here we are at 6 at time 0, right? Each unit, we're going to make a doubling. So where are we at 35, or year 35? We've doubled once. Where are we at year 70? We've doubled again. So notice what's happening here in the vertical axis. They're not 1, 2, 3, 4, 5. Each unit is a doubling. And what do we do here? If I did this right, we've made this a linear relationship. Instead of having units on the vertical axis, we have ratios. In this case, a doubling. You can have a ratio scale of 10, you can have a ratio scale of 100, you can have a ratio scale of 24 or 13.5. I mean, you can do a ratio scale, whatever ratio you want. Usually it makes sense to do simple ratios, right? Because those are easier to understand, a doubling or 10, 100, 1,000. But notice how we turn this ugly nonlinear relationship into a linear relationship that allows us to visualize what's going on. And now what do we see? It's easier to see a couple of things. It's easier to see the constant trend growth that we have here. And the scale is not distorted like it was in that one example I showed you, like in this one, right? If we try to squeeze it all into our graph, what it means is that the scale gets really distorted down here. We can't see anything. So we get to see the constant trend more easily, and the scale is not as distorted. And this is important, and particularly important for long periods of time, because remember, over long periods of time, you're going to have huge differences between level in the last period and level in the first period. And so what that means is it's just going to be very difficult for you to see what's going on, right? Very difficult for you to see what's going on. Instead of having me graph these things, let me show you some examples of how a ratio scale can really help you visualize much, much better what's going on. So first off, let's just look at growth in the United States. This is growth in the US in a typical units scale, right? So just typical scale. So notice here that there's some real problems with this graph though. Can you really see the changes in these early years, right? Is it really easy to see what was happening, for instance, between 1880 and 1900? No, because the numbers at the end are so much bigger than the numbers at the beginning. Everything at the beginning is just squeezed down, right? So it actually looks like you might, if you were not attuned to these things, if you were just kind of naive, you might look at this and say, boy, that's interesting. There was hardly any growth going on in the United States till about 1940. And then growth starts to happen. But that's a misleading because the graph itself is misleading, right? Because we haven't adjusted for scale, it makes everything in the early periods just all smushed together. It's really difficult to see what's happening. And then it makes everything out here at the end look so much more important. So a much better way to visualize GDP growth over time is to do a ratio scale. And so this is what the same thing looks like in a ratio scale. Here the ratio is a doubling, right? So every unit over here is a doubling from 4 to 8 to 16 to 32 to 64. And notice here how this looks much more linear, right? You can see the constant trend, and that trend is a little bit less than 2% a year. You can also visualize much more easily the changes in the early period relative to the changes in the late period. So for instance, if I looked at this graph, I would say, boy, early US history output was not very volatile at all. And then recent US history output is really volatile. But when you put it on a ratio scale, you reach exactly the opposite conclusion. You can see how much more volatile output was before 1920. And you can see how relatively stable output has been since the 1960s. So once again, putting things on a ratio scale is a much, much better way to visualize what's going on. This is also very useful to us when we compare across countries. Why? Because once again, there's such big differences in income levels across countries that sometimes it's impossible to see what's going on. If I just put, for instance, this figure 3.6. This is data from the United States, the UK, South Africa, Japan, Argentina, China. If I just put this on units, what would it look like? We wouldn't be able to see anything of China until about the year 2000. Why? Because Chinese GDP is so low relative to the US. So it would look like China's at 0 and then it just starts popping up. So once again, what you need to do is you need to put it on a ratio scale, which kind of lets us smush the data in a way that we can then more clearly see what's happening. So once again, the ratio scale here is a doubling, right? A doubling ratio scale. And in a ratio scale, it's much easier to see what's happened to income across these countries, given the vast differences in income levels. Right, so here it's a lot easier to see that we have between the US and Britain and Japan, we have convergence. And then between the US and Argentina and South Africa, we really have divergence, right? Notice that the difference between the US and Argentina and the US and South Africa is actually getting bigger over time, right? Here's another way that you can use the ratio scales. This is a more complicated graph, but it has some real information for us. So this is looking at where a country was in 1960 versus how fast it's grown since 1960. So the horizontal axis is how rich the country was in 1960. And then the vertical graph is how fast it's grown since 1960. Now, here's the interesting thing about this graph. How rich a country is expressed relative to the US. So the US is 1, and if a country has half the income of the US, it's going to be 0.5. But notice here how we've put this, once again, on a ratio scale. Why did we put this on a ratio scale? Because so many countries are down here at 1/64th, 1/32nd, 1/16th. They're so small relative to the US that if we just put this like 1/64th, all the countries would be jammed here in the corner. We wouldn't be able to see anything. So here, putting the data on a ratio scale actually stretches out what's happening, right? The doubling is 1/64th, 1/32nd, 1/16th, 1/8th, 1/4th, 1/2, 1. This really stretches the data out so we can more clearly see what's happening to these poorer countries down here that are, 1/8 or less, which is really most countries, or at least a big proportion. And so what do we see here? It's not a particularly strong relationship, but it does appear that countries that are richer in 1960 have grown faster since 1960. In other words, that would be divergence. That countries that were richer in 1960 have grown faster since 1960. But you'll notice here there's a lot of noise in this graph, right? I wouldn't say this relationship is particularly strong. So while there does appear to be some sort of mild divergence tendency in the data, it's not super strong, right? It's not super strong. One last graph I want to show you, and then I'm going to let you go here. Here's a very similar kind of graph, but instead of looking at growth rates, we're looking here at the share of the world's population that lives at this income level. So once again, the horizontal axis is what's the per capita GDP in a country relative to the US. And it's on a ratio scale, so we stretch everything out. So this is asking what percent of the world's population is living at 1/128th or 1/164th or 1/132nd of US GDP. This actually has two sets of data, what the world looked like in 1960 and what the world looks like in 2017. This is a very positive graph, right? Because notice how in 2017, the graph has been shifted well to the right. What does that mean? More people are living at a higher level of income in 2017 than in 1960. So in 1960, notice how many people were living at less than 1/28th of income. In 2017, almost nobody is living at less than 1/128th of US income. Many more people are up here at 1/8 or 1/4 or 1/2. And this is primarily, as the graph nicely highlights for us, because of India and China. India, right, if you see where India was back in 1960, India was down here. India is that straight part of the green line. Now India is way up here. That has shifted a big part of the graph to the right, meaning to higher levels of income. Likewise, China was way down here, and now they're shifted way up there, right? So largely this graph is driven by India and China. So you might say, well, that looks like convergence, right? Isn't more people living at a higher level of income convergence? Well, the difference between this graph and this graph, think about it. This graph is focusing on countries. This graph is focusing on individuals. So as individuals, the world looks like a much better place. Why? Because so many individuals live in China and India. But if you just use countries and China and India just become one dot among many, it looks like divergence. So this really reemphasizes the point I was trying to make this morning is when you look at the data of growth, time and time again, China and India come up, right? Because what's happened there has been so important. And because these countries are so large that while at a country level, the data doesn't look very good. It looks like there's just as many countries that are poor as used to be poor. At an individual level, things look much better because two countries that are better off are the two largest countries in the world, right? And so, you know, there's better news in here than it would first look at, for instance, on this graph. Okay, well, that was kind of a lot of math and data visualization, but I wanted to talk about that this afternoon because I think it will make going through chapter 2 a lot easier, and also to just get us thinking about this. The more practice we have with some of these little math tricks, the better we'll get at it by the end of the block. So, all right, so that's the main thing I wanted to talk about this afternoon. Anybody have any questions? So I will send you an email in a couple of minutes, and the email will basically say we're talking about chapter 2 tomorrow, and we'll have links to the lectures from today. All right? Any other questions before I let you go? All right. Thanks, everyone. We'll see you tomorrow morning.